Welcome to Boson Buzz, where we dive into the coolest scientific ideas and breakthroughs shaping tomorrow's world. We are living in the final years of the classical computing age, an era defined by the steady, predictable logic of the silicon chip. For decades, this binary language of ones and zeros has built our modern world, from smartphones to global networks, but we are now hitting a fundamental and immovable wall. The most profound challenges of our time, designing new life-saving drugs by simulating molecular interactions, creating revolutionary materials, or optimizing global supply chains, are problems so vast that even our most powerful supercomputers would need millennia to solve them. A classical computer is like a person trying to understand a symphony by reading only the sheet music for a single violin, one note at a time. It is methodical but utterly deaf to the emergent harmony, to the intricate simultaneous interplay of every instrument. To solve the universe's most profound puzzles, we need a machine that can listen to the entire symphony at once. This has been the grand, elusive promise of quantum computing, a dream long trapped in the lab. But now, a new architecture has emerged, built not on circuits, but on captured light and atoms that have learned to remember their instructions, promising a path out of this classical prison. Imagine a computer where the fundamental unit of information is not a transistor, but a single atom, suspended in a cage of pure laser light. This is the Rydberg atom array. The name comes from a strange atomic state where an atom is pumped with laser energy, elevating its outermost electron to a dizzying distance, creating a gigantic, sensitive quantum system. It is the atomic equivalent of blowing a soap bubble to an immense, delicate size. Researchers now use focused lasers, called optical tweezers, as intangible pincers to grab individual atoms and arrange them into perfect two-dimensional grids. Each atom, cooled to near absolute zero, becomes a pristine quantum bit or qubit. But unlike other fragile qubits, these atoms are nature's perfect, identical building blocks. They are stable and can be maintained in their delicate state for remarkably long periods. This system is a crystal of atoms held in a silent vacuum, a quantum gypsy, a particle existing in a landscape of probability, ready to compute. This foundational stability is what sets it apart, offering a tangible path from theoretical wonder to practical machine, a machine that computes not with electricity, but with the very rules of reality itself. The magic of this system lies in the social network of atoms. In their ground state, these atoms are solitary. But when a laser excites one into a Rydberg state, it puffs up, creating a powerful electric field, a kind of quantum personal space. If two excited atoms are brought close, their inflated clouds interact with tremendous force. This interaction is the fundamental if-then logic gate of the quantum computer. To run a calculation, scientists use a complex sequence of laser pulses to orchestrate a quantum dance. They excite specific atoms, making them interact with partners, weaving a web of conditional probabilities. In this state, each atom is in a superposition, a blend of all possible states. The entire grid exists in a collective quantum state, representing every possible answer at once. When the calculation is finished, a laser measures the atoms. The superposition collapses, and the array snaps from a cloud of maybes into a pattern of ones and zeros, the most probable answer. It is a process that leverages the inherent fuzziness of the quantum world to perform a calculation with crystal clear results. The process is a ballet of extreme precision, conducted in an environment of perfect stillness. It begins within a massive vacuum chamber sealed from all external noise. A cloud of atoms is cooled to a fraction of a degree above absolute zero, nearly stopping their motion entirely. Then, the optical tweezers activate. These focused laser beams create invisible traps, plucking individual atoms from the cloud and arranging them into a perfect, defect-free array. This grid itself is the program. Its geometry defines the problem's fundamental relationships. The system is then programmed with a tailored sequence of laser pulses, a choreography of light. For a few crucial milliseconds, the entire array exists in a special state of entanglement, where the fate of every atom is linked to every other. They collectively explore every possible configuration of the problem simultaneously, every possible drug shape, every possible material structure. When the final measurement is taken, the result is a statistical distribution. Researchers run the same calculation thousands of times, and the most frequent result that emerges from the quantum noise is the answer, a result computed not by sequential brute force, but by quantum consensus across countless parallel realities. This is not calculation as we know it. It is a form of guided evolution for information. The potential of this technology is to revolutionize any field that relies on complex modeling. The most immediate impact could be in chemistry and pharmacology. Designing a new drug is a process of trial and error that can take a decade, because simulating the quantum behavior of a molecule is impossibly hard for classical computers. A quantum computer based on atom arrays could accurately model a new drug candidate binding to a protein, revealing its efficacy and side effects before a single molecule is ever synthesized in a lab. This could slash development times from years to days and bring life-saving treatments to patients exponentially faster. In materials science, we could design entirely new classes of materials with bespoke properties, such as room temperature superconductors that would revolutionize energy grids with lossless transmission, or vastly more efficient catalysts for capturing carbon directly from the atmosphere. For global logistics, a quantum machine could solve nightmarishly complex optimization problems in seconds, finding the most efficient routes for thousands of ships and flights simultaneously, saving billions in fuel and reducing environmental impact. This is the true promise, turning today's scientific impossibilities into tomorrow's engineering realities. Despite the breathtaking promise, the path to a fully fault-tolerant quantum computer remains a monumental challenge. While Rydberg atom arrays are remarkably stable, they are not perfect. The quantum state is delicate and can be disrupted by tiny environmental fluctuations, leading to errors that corrupt the result. A major focus is developing quantum error correction codes, which spread the information of a single logical qubit across many physical atoms. This, however, requires a massive overhead, potentially thousands of physical qubits for just a handful of stable logical ones, a scaling challenge of staggering proportions. Furthermore, the societal implications are profound. A sufficiently powerful quantum computer could break most of the cryptographic codes that currently secure the entire internet, from online banking to government communications. This has sparked a global race in post-quantum cryptography. The very existence of these machines forces us to rethink global digital security. The concentration of such immense power also raises urgent questions about access and control, challenging us to build the ethical and security frameworks to contain this technology before it is fully realized, ensuring it becomes a tool for solving humanity's challenges rather than a source of new divisions. We are witnessing the birth of a new computational species, a philosophical shift from engineering computers to cultivating them from the fundamental forces of nature. We are learning to program reality at the level of atoms and probabilities. The future this points toward is one where we stop trying to brute force our way through nature's complexity and instead invite nature to compute itself, to reveal its secrets through direct participation. We are building a lens made of atoms to better see the atomic world. The journey ahead is long, but the direction is set. We are no longer just users of the quantum world, we are becoming its architects, learning to weave the ephemeral threads of superposition and entanglement into a durable fabric of understanding. This is the ultimate legacy of the quantum gypsies, these atoms that remember, holding the key to unlocking a universe of possibilities. We are not just building a faster computer. We are forging a new key for locks we have not yet been able to open, and the doors they guard lead to wonders we can only begin to imagine, from new forms of energy to a deeper comprehension of the cosmos itself.
If you found this as fascinating as I did, do me a huge favor and hit that like button. Share this video with anyone who loves science or just cool futuristic tech. And of course, if you want to stay updated on this and other amazing breakthroughs, make sure you subscribe to the channel. Thanks for watching, and I'll see you in the next one.